Hello everyone and welcome back to the Kia ora Theatre at Linux Conference Australia 2022. Next up in this slot we've got Matthew Oliver, who is a senior systems and software engineer working at NVIDIA, where he primarily works in upstream OpenStack as a Swift core. Today we're talking through the benefits and challenges of integrating OpenTracing into OpenStack Swift. Now we're going to try and have time for questions, but if we run out of time there will be follow-on question time in the post-talk chat Kia ora Theatre, accessible by the left sidebar in Venueless. It's all yours, Matthew. Take it away.
Thanks for the introduction. And yes, I say we might need to. There might be. I tend to waffle on a bit. I go off on tangents for those who know me, and I'm going to try and keep it crisp and quick. So this talk all started because I was trying to benchmark Swift on some new hardware at NVIDIA, and the way Swift is made, it's all modular, and I wanted to be able to start tracing, and so I want to start timing between these middlewares. We'll get all this in a sec, but I then showed our SRE guys, they loved it, and it's kind of snowballed into this whole tracing thing, and it's upstream, so we started working on upstream. I'm trying to figure out why am I not going to the next slide, and there we are. So, like I said, my name is Matthew Oliver. I work at NVIDIA. On all the socials, you'll see me. I'm usually up as Matt Oliver AU. I've been involved in Swift since 2014, and I've been a Swift core since 2015. So I've been doing it for a while. I'm going to tempt the demo gods today, and half my talk is going to be a live demo, or locally here, but it's going to be interesting. But before you guys can start looking at the fun traces, I want you guys to understand what you're looking at, otherwise it's not as exciting. It won't be as exciting as it is for me. So I'm going to try and bootstrap the audience into understanding. So we're going to go through this really quickly because I want to get to the fun stuff. So let's start with, what is Swift? It's a fully open source end-to-end object storage solution. It can be standalone and integrated into your environment. This is what we do at NVIDIA, or a part of the rest of the OpenStack ecosystem. It's highly extendable. It's mostly written in Python, and it is written in Python, so it's very extendable, but that's not the only reason why it's extendable. We'll get to more on that a little bit later as we look how traces work. Basically, it's done with Whiskey, so you can insert middleware you want. Where it's not written in Python, stuff like erasure coding, it's done in C. It supports the Swift API. You'd hope it does because it's Swift, and also the S3 API. You can do replicated or erasure coded policies. It's great at scale. It turns out bigger the better. We're massively scaling it at NVIDIA. In fact, we've hired a bunch of the Swift cores to make these bottleneck huge scaling issues kind of go away, get better and better. So it's actually a really fun time and a really fun community and fun problems we're solving. The upstream community is actually really awesome. There's a reason I started in 2014, and I've gone through different roles in different places and stayed in the community because they're awesome. So if you're a dev, an operator, you write docs, you're kind of just interested in the space, you just want to hang, it's a really awesome community. Anyway, let's keep moving because otherwise I'll run out of time and we don't get much time for questions at the end. So let's have a brief look at the Swift topology. We need to know this because when you start looking at traces and we're jumping around through the cluster, you kind of want to know what you're looking at. So we'll talk about the very basic Paco installs. These are what you tend to see on really small deployments, where every node has all the Swift services, the Swift proxy server, account server, container server, and object server. But then as you tend to scale up, people tend to start doing this. They start splitting out the proxy from the storage system. And this makes perfect sense. The Swift proxy is stateless, and so it's perfect for containerization. And if you put more of them in, if you want more throughput and handle more connections, you just scale them. And if you want more storage, you scale the other side. It's pretty straightforward, right? The Swift proxy is also, if you're doing things like at-rest encryption, the Swift proxy is the one that's going to be talking to, is the one that's talking to getting the encryption keys and stuff. So it's also nice to have that separated. And then you just get an encrypted stream heading to the storage nodes. Anyway, I told you tangents is what I do. So I should have got someone to like ping me or hit me when I start going off on a tangent too much. Okay, so at greater scale, this is what we tend to see, right? So when we get even higher, it's an object. Swift is an object storage system, so 99% of its storage is objects, and so having just being able to separate those object nodes away from the rest of the cluster. I mean, you know what I mean. Isolating those makes sense. The account and container side of it is our metadata layer in Swift. It's keeping track of ACLs and other metadata and other stats. Like an account will have a list of containers, and the containers will have a list of objects, and we'll have all the ACLs and metadatas and anything else and other aggregating stats up the stack. So you can think of the AC layer we see in this diagram as the metadata layer. So it makes sense to do this nice separation. This is what we do at NVIDIA. There's also, when we scale, Swift also knows about other availability zone issues too, but we're not going to go into any of that stuff. We don't have time. So here's a quick look at what happens when Swift, when we get a basic request. So I think my mouse works. I'm assuming people can see my mouse do stuff, but maybe you can't. I don't know. Anyway, I'll assume you do. So the request will come in and hit the Swift proxy, and the proxy, this is obviously going to be with an object put on probably a 3 times replicated system. So what will happen is the request comes in, the Swift proxy will look up on modify consistent hash ring for that policy of which storage nodes are responsible for storing that object, and we'll make 3 connections. Anyway, we're going to see this in a trace. This is the only reason I bring it up, right? And here is a snapshot of trace. This is not live, obviously. This is a snapshot of our trace, just to give you an idea of what you've learnt so far. So the blue here is the proxy server, and it's making an object put. And so it's making 3 connections to 1 object server, 2 object servers, and 3 object servers. Now, you can also follow along that over here, you can see over here is a container server. And so the object is being put into the object server, and then it's going to go update that metadata layer. And so we can see this in a glance, which is kind of cool. And we're getting our knowledge. Now, we'll quickly talk about OpenTracing. I know this slide goes against all what you should and what you shouldn't do with slide presentation, because there's way too much information on this slide. But I put it here in case you're interested and you get these slides and you want to go back and have a look at stuff. So we'll go over very quickly. So the project information for OpenTracing is opentracing.io. It's available in 9 languages. I obviously use Python because that's what Swift is. And basically it's an API specification, frameworks and libraries that have implemented that specification, and allows us as developers, especially open source developers, to be able to instrument our code using APIs that do not vendor lock us in. No one likes vendor locking. But what's even better is if other projects are using OpenTracing, now we can start integrating with each other and start tracing. Let's not think of Swift. Let's see the greater community, the greater open source environment. Anyway, the concepts and terminology. I'm only saying these because I will accidentally spout them out, and you guys may not understand what I'm talking about. So, concepts and terminology. So, there's a tracer. So, when you're instrumenting your code, you're dealing with a tracer all the time. And the tracer creates spans, more on that in a sec, and keeps track of the active span. It's kind of important. It also does a few things. It injects, which is really serialized, and has a term extracts, which is really deserializing the tracing context, and so we can move it across through process boundaries. A span, let's move back for a bit. So this is back a slide. Don't you come up. No, here's a slide. So we can see that this is a span. Each of these lines represents 1 span. And this whole inject extract thing is when I get to the proxy, Swift proxy, and I want to send a request to a different server or a different process boundary, then I'll be able to inject this context of the trace and then send it off. And then in this case, the object server can pick it up and continue the trace, and then we can knit these things all together at the end. And so a span is the basic building block. It references other spans. It kind of has this parent of, child of. If we go back again, I'm sorry for jumping around so much, but you can see that this span has a child and this child has a parent. It keeps track of the tree, I guess. It has start and finish timestamps and has things called tags, logs, and baggage, all of which are key value pairs. The only real difference is a tag is can be filtered by or queried, and so it's useful for when you've pulled out the trace. They expect you to use standard tags, which makes sense, stuff like HTTP method and status code and stuff like that, so we can all use the same tags across a trace, or custom. So in Swift, we tag every request that goes throughout a cluster. Every request gets a unique transaction ID. So in our case, having that as a tag makes perfect sense. Logs are just key value pairs, again, that are just stored with the span, so you can pull information out. I guess another example that I like in the Swift deployment, Swift version of this, is a proxy server is smart enough to, when it has trouble talking to a node, it can update it as it can error limit that node for a certain time. Now, when you're coming back and you're doing a trace because you're trying to find a problem, that's the kind of information you want to know about your cluster. So it's a perfect thing you can pull in and get a snapshot of time in your trace too. And the other thing is baggage. Now, baggage, it's a funny name. It allows you to predict these key value pairs, when injected or when serialized, are stored with that serialization. So it means you can do some communication between traces, which is between tracing entities, or between processes, between whatever you want to call it. Okay, I probably rambled on way too long then. Quickly, we talk about whiskey because it's going to make sense. When you look at one of these traces I'm going to show you, there's a lot of spans, and most of them are because of the way Whiskey works. Whiskey is a Python REST framework. Where I won't delve into too much details. Pictures are worth 1,000 words. So in essence, here's a very basic example. It's built up of a bunch of middlewares and an application at the end. And as a request comes in, it'll work its way down the chain and then back out and send that back the response. Now, a middleware, you can interact with the request as it comes in, when a response comes out, or you can I call short-circuiting it. So you can, for this example, we say that third middleware is an authentication middleware, and it may have gone talk to your LDAP server, whatever you want, and said, no, they're not authorized, send 401 unauthorized back, and we don't actually have to make it all the way to the application. Here's a cut down version of what this looks like in the Swift proxy server, just so you can see that nothing's rocket science here. In fact, you also notice that a lot of the Swift features are middlewares in their own right. So if you want to not have any rate limiting, I don't know why you don't want that, but say you don't care about rate limiting because the system's all for yourself, you could just remove that middleware from the pipeline definition, which is just a list of middlewares. And we wouldn't talk about it. The request would skip it completely. So that's really cool. There's also where that extensibility comes in. So you can write your own middleware that inserts your own business logic and inserts that, and you can insert it anywhere you want. So you can do something on a request as it's coming into the proxy, or when it comes back out, or better yet, it turns out the Swift account server, container servers, and object servers are all Whiskey and have their own pipelines too. So you can even insert a middleware to do something before it hits disk or when it comes out. So Swift is highly extensible. It's pretty cool. Here's another trace example where it shows this. This is an authentication to our temp auth system, which is only for development. But you can see, now we look on this side, we can see that it's walking down through the list of middleware. And we can actually watch it chain along, working its way down, and then walking back up the chain. Never made it to the application, never made it to the proxy server, and walked its way back up and returned a response. So we're almost at demos. This is the exciting bit. We're almost at the exciting bit. Thanks for sticking with me. We've been going for a while. So let's see. So high-level integration. So like the rest of Swift, it's done similarly, well, I am a Swift developer, so it kind of makes sense. It's basically middleware that we insert, and there's a trace mix in for that all the middleware's inherit because it helps. And I'll explain in a sec. So the trace middleware, as it comes in, will be inserted in the pipeline of all the storage nodes too. And when a request, its sole purpose is when a request comes in, it is to decide if tracing should start or not. It's also, I guess, it's also to note that because it starts and stops tracing, that anything to the left of it, so the gatekeeper here, it won't show up in any traces. So it's good to have it as far left as you can go. Gatekeeper is always in the end in Swift because it stops yuckiness getting out. Data you don't want it getting out. So the request comes in and hits a trace. Now there's three ways that the tracer will start a trace. So the trace middle will start a trace. And the first one is, have you given it a specific HMAC signature? So the whole purpose of this, for our use case, is we have a customer who's having issues, and at the moment, usually they come tell us they're having issues, and we look at the logs, and Swift does great logging, but sometimes there's still that level of read the logs, come with a hypothesis, and then they go test to see if that would make sure that's correct or whatever. But with this tracing middleware inserted, we can go give that customer, user, whatever, HMAC signature to attach to the end of their query, and as soon as the trace sees that, it'll start tracing. And it'll work its way, my mouse is gone, it'll work its way back up this chain, and then work its way back down, and then stop tracing. So that's one way of starting tracing. The second way is a continuation from that. So once we get to the proxy and we're making those additional requests out to storage nodes, we like I mentioned before, we inject the tracing context, if it's tracing, into the request. And so that's the second type. So if a trace middleware sees that there's an injected trace context, it knows to continue tracing. The third is what I'm using in this demo because I'm lazy, and that is log every X request in essence. And I'll have it set as log every request because I want to test. But obviously this could be like you want to do a health check, so you might want to run it every 1,000 or 10,000 or whatever you want, you pick. And so there are the three ways. The trace mix-in just means a whole bunch of helper methods are available for instrumentation to each middleware. It automatically starts a trace as it enters and ends the trace. Oh, sorry, not the trace. Starts the span when it enters and ends the span context when it finishes, and that's why we just for free get that nice graphing, the tracing. And other than that, it just helps. Oh, the other thing it does is also it calculates the response, the status code as it's of the response. We do this through the line because things like the S3 API, they might return a different response code for status code for different APIs than what Swift does. So it's nice to be able to track what it was at a certain point in time. That's just an example. So the high-level integration, this is the HMAC signature I'm talking about. This is the same slide as before, but just annotated. And so the trace in this case is going to come in, hit the Swift proxy, go through that pipeline. It's going to see this HMAC signature, which is time limited, and then we'll start tracing the request as it's going to send, inserts a trace context. It's pretty straightforward. So without further ado, we can do some demoing. So let's see if this works well. It is LCA, so take it all with a grain of salt. I'm using Jaeger tracing because it was just a Docker install away. They implement the OpenTracing API, so it just works, right? When I say just works, I had to make a tracer. This is a document that I created for the OpenStack PTG. So if you want to have the exact same environment that I have, I'll give you a link. And in fact, the link to this Google Doc is in my is in these slides. So this is the whopping amount of Jaeger tracer code. I think it's after imports, 3 lines of code. So yeah, it's very easy. And that's because this is the whole advantage of OpenTracing. Okay, so this is Jaeger tracer, and this is what we're going to use to show some examples. But first, we need to actually make some thing. So let me go to a terminal and step one. This is a fresh Swift all-in-one, virtual Swift all-in-one, a demo environment, a dev environment that we use. So I'm just going to do that. That's just going to use the Swift command line tool to run an authentication. And then, I'm sorry, I'm lost. We should see a Swift. And if we do find traces, we have our first trace. This is the transaction ID. We know it's a get, and if I click on it, this should look very familiar because it's an authentication. So you'll see it worked its way down to temp-auth. Sorry, this screen is a little bit smaller, so whatever. So we see it's what we saw before. But if we like look at the first line, we can start looking at all these tags. So we've got it was a get, it got a 200, its URL was the temp-auth URL, and we have logs and stuff like that. Very exciting stuff. But let's look at more interesting things. Sorry, be there a sec. So let's see. So next, we'll quickly put in, let's put a container because we need somewhere to put objects. So I'm going to put in just a container called C because I'm lazy. And I have no imagination on naming. And at the same time, I'll put in an erasure code. Oh, come on. Apparently I can't. It would be fast if I just type this. I'm having trouble copying and pasting. And so we can see these transactions happen. We've got some transaction IDs here, 4359 and 436B. If I go back here and do a find trace, here they both are. First one has 175 spans. There's a reason for that. It's a lot. One, it's more that code path in Swift have got more instrumented than the EC the container. But also because this is, like I said, this is a clean, brand new Swift environment. So the temp-auth is going to create, the account doesn't exist, so it's going to have to create it. So you see this really long line. The first few are probably going to be like, hey, does this account exist? Say it's an account server and it's getting a 404, so the account doesn't exist. So there's a whole bunch of extra effort going on here because it has to create these things. If we go look at towards the end, we should see it actually putting, so many. We should see it actually starting to put this container server in, and then it's going to go update the account server metadata. So we can watch that happen, and it should happen 3 times because my container ring has 3 times replication. Now I'll show you the same for this one. It should be less because it's still very long. It looks like maybe my mem cache is either ejecting things really quickly because you would have thought that would have been cached. But hey, see, here's an advantage straight away of kind of getting to know what these traces look like. You can start seeing a long line problem. I guess another thing to note is the stuff that I'm putting in are kind of or kind of junk objects, right? Like, well, I haven't put an object in. Let's do that. So that first container was so many spans because it said, hey, does the account exist? No, it doesn't. So I'll go create it. Does the container exist? No, I'll go create it. And then finally go create it. So there's lots of extra requests that usually shouldn't happen. But because it's a nice new greenfield system, that's what happens. So let's I'm just trying to copy. I'm really struggling with my copy and pasting today. I blame doing this live and not in a video. Sure. And so now I'm just putting an object into the C container, which is replicated. And while we're at it, let's put one into the erasure coded one, which I think I called EC. Now, these are silly objects. They're 4 bytes, aren't they? They've just got like 1, 2, 3, 4 in them. So, especially for erasure coding, you wouldn't want to erasure code 4 bytes. It's a little bit overkill. But anyway, let's see what happened. So if we find these traces now, we should see 2 new puts. It doesn't really matter. One's a bit more. Again, hold on, these are objects. So this is correct. Okay, so we put an object in. Let's see what this first one is. It is Yeah, okay. So this should have been cached, because in our memcache server we should already know that auth test kind of exists. So there's a bug, or there's a memcache setting issue on my dev environment. But I'm glad I can see that. So the important stuff here is this stuff then, where we're actually putting the object in. Testo, and again, because a standard object. By default, I've got my default policy as a 3 times replicated. We should have 3. So that's not as exciting. What is more interesting is some of these other spans that I've created. So, well, you can't read it. So this is a span. So I've instrumented the path going through. So there's a store object method, a bit like flame graphs, right? So it's getting put connections. It's gathering all the connections to the storage nodes it needs to be able to put this. And there's connect to the one node, this one that connects to another node, and we see the nodes interleaved in, which is nice. Down here, we've got check for failure, put connections, transfer data. Well, there's 4 bytes, right? So that's not going to do anything. And then we've got get put responses. The whole idea is, was that durably written? If it wasn't, it would go out and make another connection, that kind of stuff. Looking at the EC one should be identical, except it's an EC policy. And I think the policy was a 4-2 policy. That's 4 times, what's that, data, and 2 times parity. So we should have 6 connections. So we have 1, 2, 3, 4, 5, 6. And we've got the same kind of stuff. We're transferring data. Takes longer. Well, actually, is it taking longer, or is it... There's less data to send, but there's actually more because it's 4 bytes, and so there's a bit of overhead. This is why you wouldn't use erasure coding on a 4-byte object. But again, I don't want to go off on a tangent. And we can also see doing updates. And so there it is. It's doing a put to the EC container. It got a 201. So it's kind of fun to watch what it should look like. But they're not all that super exciting because it's just putting some objects in. I mean, that is the main, I guess, reason for an object storage system. Let's try and get that EC container back out, object back out. So for putting, we obviously had to write to all 6 nodes. When we're getting, on the other hand, it only has to talk to 4. So we should see 4. 244BE. I don't know why I'm trying to confirm transaction IDs. They're always going to be at the top. And again, it seems to be doing these damn, is it? Yeah, it's doing auth checks. My memcache is not working, and that's weird. But hey, I guess so if you're going to have a demo failure, it's good to see an error that I could see is wrong straight away. I guess that's the whole point of tracing. And if that's the only problem we're going to get, then hey, that's great in a demo. So we're connecting to 1, 2, 3, 4. So only if it's connecting to 4 to be able to rebuild this object. Also, it doesn't have to go update into the metadata lake, so we're just getting the object. We're not like adding or deleting or doing like a create, remove operation. Okay, so that's all great. That's all exciting. But let's do some more interesting ones. I should probably do a time check. Yeah, it's good. So let's go back to the slides. I don't know why that slide didn't come back. Where are you? Have I lost my slides? No, there they are. They're just not listening to me. Let's look at some more interesting features of Swift now. So the first one, let's do a bulk insert. So bulk insert is an interesting middleware. It allows you to, or feature, I guess I should say, what we know is implemented as a middleware. It allows you to upload something like a tar file, excuse me, and it'll extract it and store all the contents as objects inside your cluster. Now this is kind of cool. It's very serial. It's cool because it's kind of cool. The con is it's serial, and so if speed's an issue, you wouldn't use this feature. But if you wanted something to run in the background and you're just doing it for like, archival purposes, then it's kind of cool. So let's see what this looks like while we trace it. So in this directory, I'm just going to type it. I've got to extract tar.gz, and it has a subfolder called extract, and it's got a bunch, 4 files in it. Some text, monorail, cat, dino, and whatever. Some other random text files, because I'm lazy again. So what we expect to happen is it will go and create a container called extract, and then inside that container, it'll have all these objects, which is kind of neat if it works. And I have bulk insert. I've got it here if I can copy it, and I can paste it. So here's the command will do it. We're saying extract archive. It's a tar.gz file, so you're saying here's a tar.gz, and go do your thing. And I'm using curl instead of any other things because you can see you can easily talk to Swift. So we can see here that it was successful. We got a transaction ID. It created 4 files. The response code was 201 and there were no errors. So that's great. So if I come back here, there's 352 spans. So we know it did a lot. We can see all the things that different servers that talk to. They're all local on this laptop, on this virtual environment. But we can see, right? We can see that it's one of these should be go and create that container, that extracted container. If I scroll down to it, it's put to extract. Yeah, so we're making we're putting the extract container. That means these guys. Which one would be our monorail cat? So it would have been the second one, I think, right? So let's go look at this one. This one, in theory, if it did it in serially, like I think it does, this should be monorail cat. And it is, it's monorail cat. And so you can see from here that it's a pretty cool feature. It will go, it starts extracting it and then starts making new kind of sub requests out to all the clusters. And each of them are, because I just put it into, by default, my default policy is replication, is the replication ring. It is only 3 times replication. It's not erasure coding it. You could obviously point it to erasure. You make it create an erasure coded container to store objects in. Okay, another time check for me. Okay, we're getting toward the end. There's lots more. I could talk about this for hours. There's lots more I could talk about, but and you ask the guys at the PTG. I just kept on going. But if we go to the next one, did I go too far? I don't know if I think listening to me. Nope, I don't got a conclusion. Go back. There we go. So another interesting feature from the other side of things is static large objects. So the idea here is like MTU multi-part things in AWS. So you have your object, you can divide it up into what we call segments, and you upload them separately. So again, hit different Swift proxies. You can do it concurrently. You can do it quick. If it's a really large item, you can cut it into thousands. If it's a smaller item but you just want to upload it quicker, then this is a way you could do it. And then at last it will send a JSON manifest to stitch it all together. So when you go get that JSON manifest, it will then be able to pull these and stitch these back together for you. So we can see that in action. Now I'm going to use this. This is why I'm not going to use curl, because it's a little bit more involved. So I'll just let the Swift client do its thing. So this command is saying Swift upload, use SLO, what's that, about 5 meg-ish chunks to my 10 megabyte image, which is, I think I did it by urandom, so nothing useful. And it uploaded 3 segments. I'm assuming it's five-ish and a little bit. And that last, so it's made 1, 2, 3 requests, and the last request should have been inserting manifest, which has the name 10mb.image, because that's what I told it I want it to be called. So if we go look at this in our trace, it won't be super interesting because it's going to be a bunch of extra new requests because it's inserting one each time. And we've seen inserting an object. The last one, we'll confirm that the last one is in fact, actually I'll just look at the top here, is in fact sending in the manifest file. What's more, this is my favorite bit. So what's more interesting is if we try and get that object back out now. I'll just use the good old cut and paste, because I don't think you want 10 megabytes of random crap on my screen or on the dev. So we downloaded it. I don't know what the transaction ID was, but it turns out it doesn't matter. Here it is. It doesn't seem like much, but look at it. It's a bit of a crazy, up here is the full kind of time separated request. And it's interesting, right? Like, so what it's done is it's gone to do a get of the manifest. This should be a get of the manifest file. Yep, good. We're good. I do know my stuff. That's good. And then it's starting to build. So what Whiskey does? Let me see the time check again. Cool. So what Whiskey does is it will send back the response headers and stuff, and it will wrap up the body in a file like iterator. And so it will send back all that to the client, in this case curl, and then curl will start reading the body to the body of the request. So we can see it is getting that manifest file. At this point, it's actually probably going to go get that first segment, just getting that iterator ready, the file like iterator ready. Yep, it's getting segment 0. I'm pointing at a screen that you can't see me point at. Use the mouse, Matt. Use the mouse. 0. First one, 0 based, because it's programming, because it's IT. And then there's this big gaps. This gap is caused by curl. So as curl reads, as it's dealt with the first segment, it reads and then gets a second segment, and we can actually see this happening, and it's kind of really cool. Well, I think it's really cool. I get excited about this stuff. I don't know if you guys do. But I definitely do. I can do other things. Let me see how time goes. I think we've probably only got, 5 minutes before I want to try and stop for questions. So let me finish the last few slides of the presentation, and if we want, and if anyone's interested, I can go, because I've shown you all the happy path things, right? We can also go in and go kill a server and then do requests and see what the traces look like. This is where all the fun stuff, because let's be honest, when you're doing a trace request, you're not tracing the happy path, you tend to be tracing because of an issue, and we can try and demonstrate that stuff. If only we had more than 45 minutes. So, conclusion, I wrote this up an hour ago, so it's a bit more verbose. Being able to visualize a request, at least to me, has been amazing. I've been involved in Swift for a long time. I know how the code works, and build up my mental model. I know what's happening, but to see it, it's like seeing your baby. Well, maybe not that far, but it's like it's being able to see it has actually been really exciting for me, if you can't tell. And I also think that the human ability to pattern match means we tend to spot potential issues quickly. I guess, and I saw it before, right? I saw that things are not being stored in memcache like they're supposed to be, so we saw an issue. But that only comes down to, you need to know what normal looks like. So there is going to be a level of having to train. And this is where our SREs are at in NVIDIA now, that we've got some dev environments. We haven't rolled it out to full production yet. It's more in some of our staging environments, so we can get an idea of what these things look like and get it integrated into our what's the word? I can't think of it. Our ProStack, our monitoring. There we go. That's the word I'm looking for. Our monitoring stack. But so first is learning what normal looks like, because if you don't know what normal looks like, then the pattern match doesn't work. We can see what happened in a request rather than hypothesize. Maybe you guys are good at, and SREs and you sysads out there are amazing at being able to figure out what happened from logs. And I struggle sometimes. But being able to actually look at what happened at the time and being able to pull in information. And yes, we're not pulling in all the information yet, but there's the code there. And in that mix in there, we can continue to instrument the parts that we need to pull out the information we need. And just nice to have another way of pulling out information. Get back to those error limited nodes in the Swift proxy server. We do dump those to logging if you turn your debugging up to debug, but in production we don't want to do that. Especially on really, really, really large clusters. So being able to have a way of pulling that data out, it's kind of exciting and interesting. There were a few interesting problems that we had along the way. This is maybe more for people who are Python developers who have had to deal with eventlet and green threads and stuff. But weirdly, I told you that the tracer was in charge of keeping track of the active span. So anyway, what I'd find was once we get into an eventlet thread pool and out the other side, so it's in an instant threading environment, it just had lost its active span from inside the tracer. So we had to figure out ways of pinning that in because suddenly tracing doesn't work, and that's not really useful. Response iterators, that last one you saw with the SLO, static large object getting. What also tends to happen is because Whiskey kind of sends back the response with that file like iterator, it decides that it kind of cleans up all the context, all the span contexts and stuff, and so they don't kind of exist when we're still making new calls to the next segment, for example. And so the same kind of solution to the green thread eventlet seemed to here too. It's just kind of keeping those things alive, making sure we've got them pinned so they don't just disappear when their context ends. By default. And I guess the other thing is request tracing has been interesting. It's Whiskey tends to have a lot of these middlewares in memory, and a request coming through is really an event dictionary that kind of works its way around an environment dictionary. And because we're trying to keep the scope of tracing to a single request, it means the kind of tracing mechanics had to some extent, the state of them had to live inside these dicts. And it's just interesting. It got into interesting problems because we didn't want issues to bleed into other issues. Anyway, I think I'm running out of time, so I'll end this here. Well, actually, I'll give you these things. So if you want to contact me, email me at NVIDIA, at my thing there, or at oliver.au. Again, I'm on Matt Oliver AU on all the socials. If you want to come check out the Swift project, we all hang out on ISC. Not quite the cool kids anymore, I think. But anyway, we're on OpenStack Swift on OFTC. There's our project website, swift.openstack.org. There is a link to the contributing guide. You should come and have fun with us. And there's some interesting links. There's the link to this code in Gerrit as it stands, and that Google Doc that will get you bootstrapped into doing exactly what my system's doing right here if you want to have a play.
I'm really looking forward to typing that Google Doc link in.
Oh, yeah, well, I'll share this. Yeah, it is not great. Maybe I should have shortened it, but I don't think about that until...
You can put the slides into the text chat afterwards.
Okay, I'll do that. I'll definitely do that. So that's it. Any questions? Oh, actually, yes, what time do we have?
We do have a few questions. Cool. We've got 2.5 minutes to talk
through
them. Yep. So the first question that we've got is, OpenTracing is only application specific. Does it use any tracing mechanism from Linux kernel?
No, it's just application specific. The idea is it's just an API. That would be cool though, actually. If we could do some tracing down at the kernel level, I would like that too. Because there's sometimes where some of our Swift issues are not always application specific, right? When we in NVIDIA are looking at how can we speed up transfers? How can we talk directly to disk? Can we do DRMAing and all this kind of fun stuff? So being able to kind of get under the hood a bit more would be great. But no, this is at the moment open. At least as far as I'm aware, it's very application specific.
Cool. Another question we have is, what overhead have you seen having tracing going? Would you leave it on full time in prod?
This is great because this is the question I would have asked myself. So here we go. Basic benchmarks. Now you take this with a grain of salt because this is just on this dev machine and I did it during LCA, right? So, because that's the way we do things in LCA. So it's very basic. This is pretty much just 1,000 get puts and deletes. It's just 1K objects, so take it with a grain of salt. But the whole point is a similar environment. One, there's no tracing at all, no code. It's like master without this patch applied. Then we've got tracing off. That is the red one. It is got it's got all the tracing code enabled, but it does not tracing anything. And tracing on is not how you would ever run this thing. It's tracing every single request, but we want to test this stuff, right? And so tracing on is the code with tracing turned on every request. As expected, when you got tracing on, it gives us a performance hit. But it seems, at least in this small one, and we will be testing this before we roll it in production too, as we test it on our bigger staging systems, just to confirm. But in all my tests so far, it has been negligible. In a lot of the coding, if you ever look at the code, I've gone to great efforts to try and make any of the tracing stuff, if it's not tracing, as no-op as possible. So I didn't want to affect our spin. So our latency distribution. So we got 1,000 puts, or we got 1,000 puts, and most of them were identical to no tracing. There's slight differences we can see. So it will have a marginal effect, as you would expect. The ops per second, we can see that tracing on, well, yeah, it's never going to be great, right? But tracing off and no tracing are fairly similar. I'd like to do a bigger scale of this, but thanks whoever asked that question, because it's exactly the question that I was thinking, which is why I preempted. Does that answer that question? Well, the best I can answer that question right now. Is there anything else?
You're muted.
I'm muted. I'm so sorry. I've got a couple more questions that I'll jump into the text chat in the post-talk chat for Kia ora theatre, and then I will... yeah, we've got afternoon tea now. Thank you so much for your talk, Matthew. Green, great to have you. And we'll see everyone back at 3:45 p.m. AEDT for Sam Bishop with Boldly Going, Running Linux in Space.
Awesome. Thanks, everyone. I'll be in the chat.